So let's start to sort of apply that in the form of an example. So this is the old you run out of gas example. So you run out of gas and you have to push your car. Car has a mass of 1,200 kilograms. And you push it from rest to a speed, to a velocity of 4 meters per second in some direction, with an average force of 300 newtons. So the question is, how long does it take to get the car up to speed? So sort of a simplified example, but illustrating the point of what we've been talking about. All right, so the picture looks like this. You have a car, which is always a hatchback, and it's a little car that you're pushing. Not to scale. And in doing so, you're applying a force of 300 newtons to the car. Okay, so we want to know about how long does it take to get the car up to speed. Again, you could go back and you could use Newton's second law in its original F equals ma form, solve for an acceleration, use some velocities, figure out a time, so dynamics plus kinematics equals answer. Okay? Or you could do what we've been doing, we just started learning about, and take the easy route. All right, so let's take the easy route. The first thing I know is that, well, a force, if I'm thinking about forces and I'm interested in some sort of time, that sort of screams impulse, right? So remember the impulse, we just defined it. It's equal to the net force acting on an object times some time. And that's what we're after, is delta t here. We know the net force, so in order to figure out delta t, we need to know the impulse. Luckily, we have the impulse momentum theorem that says that the impulse is equal to the change in momentum. All right? In this case, we just have a pretty simple system. We're looking at the car. That's what the force is being exerted on the car. We know about the change in momentum of the car, so we can go ahead and solve this. So I'm after delta t, and that's just equal to the final momentum of the car minus the initial momentum of the car divided by the net force. All right? And if I expand out my momentum terms, that's going to be the mass times the velocity final minus the mass times the initial velocity divided by the net force is equal to delta t. My velocities all point in the same direction of the force, so this becomes a scalar equation. Because this is 1D motion, just like when we're talking about kinematics, 1D motion, we're really dealing with left or right, up or down scalars with signs. Okay? Now, I do know one thing. I know that I'm starting from rest, so that means my initial velocity goes away. It's 0, and I'm just left with a simple mv divided by f equation. So I can plug in my numbers. Mass is 1,200 kilos. The initial speed is 4 meters per second, and it looks like it's to the right as I've drawn it. The net force, 300 newtons, also to the right. And if you solve that, you get some value of about 16 seconds. So it takes about 16 seconds to get that car up to speed, which seems reasonable. Cars are heavy. Pushing them takes a while. Now, of course, we've ignored friction. And you know that if you push a car for 16 seconds, it's probably not going to go very fast because at some point friction takes over and does some work against you. But in this simple example, we're ignoring friction. So let me just add one additional wrinkle. Say that two friends come out to help. And they each apply an additional 300 newtons. So now how long does it take? Yep, so starting over from rest, how long does it take? So similar sort of problem. This time we have the car and we have 3 peoples, each pushing with 300 newtons. So the total force acting on the car is 900 newtons. All right, well, my entire setup, the entire problem is the same, so I'm just left with the same equation, which is that delta T is equal to the mass, 1,200 kilograms, times the final speed, final velocity, which is 4 meters per second to the right, divided by the total force, which now becomes 900 newtons, also to the right. So if we solve for delta T, we get a different value. It's got to be smaller because the denominator is larger, so it takes 5.3 seconds. All right, so just like I said when we started this whole discussion was, the larger force results in a smaller time. Okay, the whole idea of that, what we care about is a force and a time now. All right, so a simple problem looking at how impulse and momentum are related. Does this sit okay with everybody? Any questions? So far, so good? Va bene. All right, so let's do another sort of mixed conceptual slash non-conceptual example. All right, so this question regards designing that's not right. There we go. You design a couple of bulletproof vests. The first one, it causes the incoming bullet to bounce off the vest with some velocity in the opposite direction. Opposite of the initial velocity. So it changes direction, bounces off. All right? The second vest absorbs the bullet. So the question is, which one is better? Now, let me just ask. So what do you think? So in one case, the bullet actually bounces off, goes the other way. So you're like really getting rid of that bullet. The other one, it just gets sucked up into the vest, absorbed by the vest. It's stuck to the vest.
Second one.
So who thinks the second one? Why do you think the second one? Because you've watched enough TV and you've seen the bulletproof vest, they all absorb? Okay.
I feel like also maybe the closing linen would be subject to less force.
So what we're really curious about, I mean, when I say which one is better, what we want to do is we want to minimize the force, right? I mean, that's sort of what we're after. Lower force means less harm to our body.
So bounce it off by exerting force on the bullet. So absorbing it by force dispersed around your body. I don't know.
Isn't that also just
Sounds
dangerous?
pretty good.
What's that, Liam?
Isn't that also just dangerous to have a high-speed bullet bouncing off it?
Well, no, it'd be a great, like if anybody tries to shoot you, they actually get shot. So it's actually, I mean, as long as you can reflect things, in the right angle. It'd be like a superpower. Okay, all right, so I'm hearing good ideas here. I'm hearing discussion about force. Let's actually do some analysis and see if our analysis actually will validate our thoughts. So we have two cases. In the first case, you've got the bullet. It's coming in with some initial velocity, and it hits the vest, which I'm going to draw as a rectangle. And then it bounces off, going in the opposite direction. And it has some final velocity. Okay? In the second case, same vest, or similar vest, Bullet coming in at the same initial velocity, vi, but the bullet then just sticks right in that vest. Final velocity is 0, assuming the person doesn't fall over. Okay? So we can look at this. This is we have a change in velocity in both problems. Change in velocity screams momentum, so let's apply what we've learned about momentum. So in this case, we have a change in momentum, delta p, it's equal to the final momentum minus the initial momentum. That's equal to the mass times the final velocity minus the initial velocity. Right? I don't know anything, I'm not giving you any numbers or anything like that, but I do know the sign of my final velocity. So I'm going to write this as mass times the magnitude, mass times the negative, the final velocity is in the negative x direction if I want to call it to the right x. And then I'll just put in the magnitude of the final velocity here, just to make it really clear what we're talking about. And I'm sorry, I left off an n there.
What's next to the n?
This is a negative sign. It's just a minus sign. So I'm multiplying m times the negative, that's the direction of my velocity. And then I'm subtracting off the magnitude of the initial velocity. Right? I just factored out an m here, and then I have vf, but the magnitude of vf is going to the left. So that's my sign, that's my direction. vi is going to the right, but this negative sign comes from me taking the difference. All right? So I'm being consistent with the sign. So then what I'm left with here is just the mass. I pull out the negative sign because there's two of them. The mass negative times the mass, -1 times the mass times the difference, or the sum of the speeds. All right? Because there's two negative signs here, I just pull that out in front, and then I have a positive sign in between. Yeah?
Why did you have the negative sign in front of the final velocity?
Right here?
Yeah.
Because remember, it's a vector, so we have to have a direction. The velocity is going in the final velocity is in the negative x direction, so I just put negative times the magnitude of my velocity.
Okay.
Okay, so that's my change momentum for the first scenario. For the second scenario, I could do a similar sort of exercise. Delta p is equal to p final minus p initial. Again, they're all vectors. In this case, my final velocity is 0, which means that my final momentum is 0. So all I'm left with then is negative times my initial momentum, which is the mass times the magnitude of the initial velocity. All right? Well, this term, so my momentum in both cases, my change in momentum in both cases is negative, so that's the direction. The magnitude of the momentum change, let me see, write that correctly. The magnitude of the momentum change in case 1 here is m times vi plus vf times the the sum of the two speeds. Well, that has to be greater than mass times just the individual speed, right? If we're talking about magnitudes here. So the magnitude of delta p1 is greater than the magnitude of delta p2. So there's a larger change in momentum of the bullet in this first example. What that means then, if there's a larger change in momentum, that means that the impulse in our first scenario from our first vest, that's got to be greater than the impulse acting on the bullet in the second case. All right? Well, impulse, we know that the impulse is related to a force over a time. So what that says is that the net force acting on the bullet in scenario 1 times the time that the force is acting has got to be greater than the net force acting on the second bullet times the time. And of course, assuming that delta t is the same, that implies that this force, the force acting on the bullet in the first case, is larger, which is what you guys said. Right? So the vest is exerting a larger force on the bullet, which means that the bullet in the first case is exerting a larger force on the vest. In other words, on the person. So it is better then to be in the second scenario because the force exerted on the vest, on the person, is less. Right? So sort of validating what you guys said. And this, of course, is the reason why when you see bulletproof vests in action on TV, they absorb the bullet because that's what they're meant to do. All right, so let me make a slight extension here. In both of these cases, or at least in this case, I sort of assume that the person didn't fall. The person just stood there. So would it be better then for the person to just stand there, for the person to move forward as they're getting shot, or for the person to move backwards as they're getting shot? So backwards, right. For the exact same reason, because what I'm doing is I'm minimizing the change in momentum. All right, I'm minimizing the change in momentum, which means that I'm minimizing the force that I need to absorb that bullet. All right, if you're moving into the bullet, basically what that amounts to is the bullet, it seems like the bullet's moving faster, which of course is bad. You want a slow-moving bullet when you're getting shot as opposed to a fast-moving bullet. You always want to request that in any robbery situation. Okay? This is actually, this is real-world stuff, and this sort of idea is applied all over, all throughout our lives, all throughout the machines and the things that we do in our lives. I like to use the example because I'm a rock climber. Right? I teach people how to rock climb. Okay? Now you can imagine when you're rock climbing, people fall. That's why you have a rope. All right? So you can imagine that you've got a rock wall, and the person's up here, they're climbing, they're attached to a rope, which is attached to the wall like here, and then that goes back down to a person on the ground. And they're holding onto the rope, using a harness. All right? So when this person falls, they take a fall, what they're going to end up doing is they're going to, the anchor point's here, and they fall down so that they're, hanging out here by their neck, like so. And when people learn how to catch falls, their instinct when they see that their partner is falling is to move that way. That's sort of instinct. Oh, I got to tighten up the rope. I want to make sure that they don't fall as far. Okay? And this is exactly wrong for the exact same reasons that we've just been talking about. Because I'm not so concerned, as long as they're not going to fall and hit the ground, I'm not so concerned about how far they fall. I'm more concerned about with the force that they experience during the fall. And not only that, I'm also concerned about the force that the anchor experiences. And that's all related to the change in momentum. So if I move backwards, all right, what I'm in essence doing is increasing the speed of this fall. I'm increasing the change in momentum of the person falling. Their initial speed becomes much larger than it initially was, and their final speed adjusts accordingly, and so the momentum change is greater. So the force that they actually experience during the fall is larger. So what you're supposed to do is you're supposed to allow the rope to pull you into the wall. And as you do that, what you're doing is minimizing the force that the person feels, and more importantly, the force that the anchor feels, so that the anchor doesn't get yanked out of the wall. All right, so that's the idea, for the exact same reasons that we just talked about in the example with the bulletproof vest. Yeah, Chooks?
So is it right to say that the tension, like as the person on the bottom is moving, the tension is less on the person falling?
Yeah, well, no, that's not technically the case, because remember, tension, if we're looking at our ideal physics ropes, the tension throughout this rope is the same throughout. But in the case where the person moves to the left, the tension in the rope will be greater than in the case where the person moves to the right. All right, so if you're worried about breaking your rope, you want to have a smaller force. So you want to move into the wall so that the tension in the rope is minimal, all right, during that fall. Okay, and these are all things that you learn when you're doing more advanced sort of rock climbing. Learn about this sort of stuff. We don't talk about the physics. We should talk about the physics. But this is what, one of the big things that people don't understand. And you'll often see people when they're rock climbing doing this exactly wrong, and that's actually more dangerous to do it that way. Right? Any questions so far? All right, cool. All right, so let's keep going a little bit more today, and we'll call it quits in a few minutes here. So I want to switch colors. I want to do some more green. Green is my favorite color. I should use it more. All right, so I want to start to, now we've been talking about so far, this last example with the rock climber was sort of a little bit more complicated, but in the case of the car, in the case of the bullet, we sort of were just looking at the bullet. Now, of course, the vest was there exerting a force on the bullet, so there was a collision happening, but we weren't really considering the collision in very much detail. So we're gonna move on, and we're gonna start to talk about multiple objects in a little bit more detail. And in doing so, we're gonna come across the term I can't spell, conservation. Spelling and talking is not my strong suit. So we're gonna talk about conservation of linear momentum. And this is really when we start to get into analyzing collisions. All right, so just like energy, which we talked about as being a conserved quantity, momentum is a conserved quantity. Now, the first equation that I wrote regarding momentum in any sort of detail was this. So this says right here that the change in momentum is equal to the net force acting on an object. Now, I would postulate that if a quantity is conserved, that it shouldn't change, in your system, right? If you have some initial energy, that should be equal to the final energy of your system. If you have some initial momentum, if in fact it is a conserved quantity, it should be equal to the final momentum of your system. So there's one little wrinkle we have to throw in here. Now, when we were talking about energy being conserved, we said if there are no non-conservative forces acting on the object, then energy is conserved. If there are conservative forces, well, then energy is still conserved. We just can't really track it very well, right? So that we had to sort of take into account this work term, right? So the same thing here is momentum is a conserved quantity as long as if the net force is 0, then momentum is conserved. And I'm going to quantify this net force with one extra thing. We've talked about this a little bit, but we haven't really gotten into the details. This is if the net external force. So if there are no net external forces acting on an object, if they all balance or if there aren't any to begin with, if the net external force is 0, then momentum is conserved. And of course, that falls straight from this equation. If this term is 0, then certainly delta P is 0, which then implies that PF is equal to PI. The initial momentum is equal to the final momentum. Okay? Now, just like energy conservation is extremely important, this is also very, very, very important. And just like when I introduced energy conservation, I said that we use that equation in one form or another in all sorts of studies in physics. All sorts of different regimes of physics, be it thermodynamics or fluids or magnetohydrodynamics, if you even want to know what that is. We use the idea of energy conservation of energy directly in our analysis. It's the same thing for this. Conservation of momentum, just as important. Okay? But this boxed thing here, which you'll be dealing with a lot in your homework whenever I get around to assigning it, only applies, again, I'm stressing this, if there are no net external forces. All right, so don't forget that. Now, the last thing I want to do today, though, is sort of discuss this idea of external versus internal forces a little bit more so that we're more clear on what we're talking about there. So the real question that I'm asking then is, well, how do you recognize whether or not a force is internal versus external? So let's attack this looking at the truck and the car example. All right, so we're looking at a truck and a car, and those two objects are going to decide to run into each other. My cars are horrible. All right, so you have some car, it's moving at a velocity v sub c. You have some truck. That is moving at a velocity v sub t. And eventually they're going to encounter one another. So when they collide, the truck exerts a force on the car. As you well expect. So that means then that if I just look at the car, let me take a look at the car here. So here's the car. I could draw a free body diagram in that car where I'm labeling all the external forces. There's this force due to the truck. Since there's a net force acting on the truck, the momentum of the car must change. Right? The force of the truck acting on the car, that force, that's an external force. It's just a normal, it's a push or a pull like we've been dealing with all along. All right? There's nothing balancing that force. Its momentum must change. And as you would expect, in fact, the velocity of the car is going to change. If you've been in an accident or seen one or have been alive for longer than a year, you know that the velocity of the car is going to change. Similarly, though, we could do a similar picture for the truck, right? So similarly, the car exerts a force on the truck. So I can draw another picture of the truck. Here's the truck. It's got some wheels. All right, and the car is exerting a force on that guy, like so. And since this force of the car on the truck, that's an external force, you'd say, well, fine, then the momentum of the truck then also must change. All right, again, no surprises there. So the question then is, well, there's something interesting about those two forces, though. And you can really see what's interesting about those two forces if I take a look at the truck and the car together as they collide. So as they collide, I can still draw those forces if I want to. I can certainly do that. We're going with a light green color. I like that color. So the car is still exerting a force on the truck. The truck is still exerting a force on the car. But those two forces are related. All right? I'm looking at the system as one whole system now. How are those two related?
Equal and opposite.
All right, so Ft and F sub c are equal and opposite. Why are they equal and opposite? Because Newton said, let it be so. All right, I like to call them, some people call them action-reaction pairs. I call them third law pairs. So it's Newton's third law. For every force, there's an equal and opposite force. So those are third law pairs. And so what you can do is if you can draw a system and you can identify the third law pairs, then those must be internal forces. So all third law pairs are internal. All right, that's not to say, up here in our picture on the truck, F sub c, that's still a third law pair with F sub c, but they're not, or with F sub t, with the force of the truck on the car, but we're not accounting for them in the same picture. All right, we've separated the truck and the car. Now we're looking at the truck and the car as one system. All right, I've defined my system here with this nice little dashed rectangle. So both of those forces are within my system. They're both acting on my system. All third law pairs are internal, and that's important because since they're third law pairs, they're equal and opposite, which says that Ft plus Fc must be equal to 0. So if you were to account for any internal forces, so in our, let me write it out in all its glory. So let me say that delta P, well, that's actually equal to the sum total of all the net forces times delta T, right? That's our impulse momentum theorem. So let me say, okay, well, net force, that can include both external forces and internal forces. I mean, I didn't say anything, That's certainly a force. Those are internal forces. But the thing is, all of these internal forces, they all look like this. They all have pairs. They all have third law pairs, which means that if you add up the pairs, you're always going to get 0. So when you add up all of the internal forces, that term's always 0. It can't not be 0. If you're really talking about internal forces, it's always 0. And so the way that you can identify a force that's internal to your system is whether or not you can identify it as part of a Newton's third law pair. All right, if you can find a third law pair, then I'm not going to worry about those. I'm not going to draw them. They don't apply. They just cancel each other out. And the reason that I'm spending a couple minutes talking about this is because we're dealing with collisions. We're dealing with 2 or 3 or more objects interacting with one another. And so there's going to be lots of these third law pairs. Right? And so it's important that you could recognize when, no, that is not an external force. I'm allowed to use conservation momentum so that you can go about and solve your problems. All right? So this is sort of the key, being able to recognize internal forces. These are always 0 if F net external is equal to 0, then I can say delta P is also equal to 0. Momentum is conserved.